Hey, welcome back everyone. Welcome to another lesson. Last time we left off, we discussed how to draw the displacement time and velocity time graphs. In this lesson, we'll be applying what we learnt previously to a question. So let's say we're tracking a runner. So let's say we have some runner here. And let's assume that this runner runs at a constant velocity throughout. So in the first part of his run, let's say he covers 80 meters. And let's say that happens in 10 seconds. Then he slows down for a bit of a jog for the next 30 seconds and he covers 90 meters. So let's say he does 90 meters from point 1 to point 2. So we'll call this point 1, point 2, and this will occur over 30 seconds. Then the runner sprints back in the opposite direction for 80 meters. So let's say this is now point 3. And he does this over a period of 10 seconds. Then he takes a break for 10 seconds and proceeds to sprint back to the origin point within 9 seconds. So he goes from point 3 all the way back to point 0 in 9 seconds. So this is point 0. How do we draw out the displacement time graph, velocity time graph, and acceleration time graph? A good place is to start with a diagram which we've already created up here. We can then define a direction which is arbitrary as positive, and I usually like to pick the direction that the object initially travels in, which in this case will be towards the right. So we'll define anything towards the right of this origin point as positive. Now that we know those two things, we can go ahead and break up the motion into parts, with the first part being the sprint, in which he covers 80 meters over 10 seconds. So let's go ahead and sketch out what our displacement time graph would look like. So we've got x on our y-axis, and we got time on our x-axis. And I might just make this graph a little bit smaller so we don't draw over the diagram. So we've got x in meters. We know that the starting point is going to be 0, 0. And we also know that he's going to cover 80 meters in the first 10 seconds at a constant velocity. So we can go ahead and mark that on our displacement time graph as 80 occurring at 10 seconds. So this point here, which I'll call point 1, will be located at 1080 on the graph. And I might just take that to the other side in case we want to draw more points. So let's say 10 and 80. And from our previous lesson, we remember that any movement in the positive direction with a constant velocity is represented by a linear line on the displacement time graph. So we'll connect the origin point and this point, which is point 1, with a linear line. And that's because a linear line means constant velocity. We also know that the change in displacement over time is what velocity is equal to, so we can say v is equal to change in x over time. So for the first section, which we'll call section 1, so the velocity at section 1 will be equal to the change in displacement over time, which is going to be equal to 80. And this number will be positive because obviously we're moving towards the right, which we've defined as positive, divided by 10 seconds. So we get a velocity for this section of 8 meters per second. And we can obviously show that on a velocity time graph. As a positive straight horizontal line, because there's no change in velocity because it's constant and it's in the positive direction. So we can mark this as our first stage. During the second stage, we see that the runner jogs for 30 seconds and covers 90 meters. Since he travels a further 90 meters in the same direction, we can add that displacement onto the previous displacement to give us our new point. So we can say displacement part 2, or for the second stage, is equal to x1 plus 90 meters. And we know x1 is 80 meters. So our displacement up to stage 2 is 170 meters. And that'll be at the end of 40 seconds. So we can go ahead and put this new point on our displacement time diagram. So let's get rid of this just so it doesn't confuse us. Put 30 seconds there, and our new point will be, let's say that's 40 seconds, and this here is 170. So we got 40, 170. And I have a feeling we're going to need some more space, so let's extend this graph out a little bit more. And let's make it a bit longer, like this. And we'll do the same thing for our bottom graph, just so we have enough space. And just how we worked out the velocity before, we'll do the same thing here. So we'll say the velocity over stage 2, or this section, is equal to the change in displacement divided by time. So the change in displacement is 170 minus our initial, which is 80, divided by the time, which was 30 seconds, which gives us a velocity of stage 2 at stage 2 of 3 meters per second. So we get a dip in velocity where this our new point is 3 meters per second, and this runner runs at that speed for 30 seconds, so up to this stage here. In the third stage of his run, the runner sprints to the left by 80 meters in 10 seconds. And as we're moving in the left direction now, our displacement ends up being negative because we're running towards the origin point, or towards the left, which we've defined as negative. So our new point becomes 170 minus 80, which gives us 90 meters towards the right. And this occurs over a period of 10 seconds. So our new point on the displacement time graph becomes 50 seconds and 90 meters. So there's a point over here. We'll mark that. And that will be 50 at 90. And the velocity during this period will just be calculated how we calculated it before. So we'll say the velocity during stage 3 is equal to the final displacement, which is 90 meters, minus the initial displacement, which is 170, divided by 10 seconds, which gives us negative 80 over 10, which is negative 8 meters per second, which we can go ahead and mark on our velocity time diagram. So we've got negative 8 occurring at stage 3 for 10 seconds. The runner then decides to take a breather for 10 seconds, so our displacement stays the same, which we show as a horizontal line on the displacement time graph. So our new point becomes 90 meter displacement for 10 more seconds. So this is stage 4, and this point here is 60, 90. And because there's no change in displacement, that follows that the velocity will also be equal to 0 during this period. And we can draw that in as 0 on the y-axis, or for velocity. In the last leg of the runner's journey, he sprints back 90 meters back to his starting point in 9 seconds. So our new point becomes 0 because he's sprinting the other way towards the left, and 69 because he finishes, and the time taken to do that is 9 seconds. So the new point becomes 69 and 0. And the velocity during this stage, or the last stage, which we'll refer to as stage number 5, is going to be equal to the final displacement, which is 0, minus what he started at, which is 90, or negative 90, divided by 9, which gives us a velocity of negative 10 meters per second. So we can go ahead and mark that down on our diagram here as well, on our velocity time diagram. At which point he comes to a stop. Now, just out of curiosity, what would the distance covered be? Well, if we just add all the distances he runs, then we get 80 plus 90 plus 80 plus 90 again to give us the total distance he runs, which is equal to 340 meters. And we can verify this by looking at the velocity time graph too. If we add up all the areas under the curve, under the velocity time curve, we get the total displacement. So if we look at this area here, this area here, this area here, and that area there, let's see what we get. So for the first stage, we have a displacement of 8 times 10. For the second stage, we have 30 seconds times 3 meters per second, which gives us a displacement of 90 meters. For stage 3, we have 10 seconds times negative 8 meters per second, which gives us negative 80 meters. And for the last leg, we have a displacement of 9 seconds times 10 meters per second, which is negative, to give us negative 90 meters. So if we add all these up, we get a total displacement of 0 meters. But if we take these negatives away and add all these numbers up, we get a distance of 340 meters, which makes sense since the distance traveled is a scalar and has no direction. What if we had reversed the direction and chosen left as our positive rather than the right? Well, we'd have the same values as we did before, only that they'd be negative. So if I made the right negative, then a movement in the right direction would be recorded as negative. So for example, the first stage of the runner's movement would be written as a negative value. So it would no longer be 1080, it would be 10 negative 80, because the runner would be moving in the negative direction compared to what we had defined at the start of the question. And therefore, the corresponding velocity would be negative 2. So the shape of the graph is determined by the direction you define as positive. And all these points that we plotted out before would just be mirrored in the x-axis, like so. So I hope this gave you a clearer understanding of how we can plot motion in one dimension. And as always, I'll catch you at the next class.